Hey there, we're going to go over some static torque notes, and then we're going to work some practice problems together applying these new concepts. And the first thing we're going to do is just define what is torque. So torque is just a measure of how much a force acting on an object causes that object to rotate. So let's kind of write that out. So it's just a measure of how much force acting on an object causes that object to rotate. So that's just a basic definition of torque. Now, torque, it depends on a few things. Okay, the first thing it depends on is the magnitude of the force that's being applied. Okay, it also depends on the angle that the force is being applied. It depends on the direction that it's being applied. So a force causing an object to rotate, that direction, it's going to either be counterclockwise or clockwise. And then it also depends on the point at which it's applied. So torque, it depends on all four of these things, okay? The magnitude of the force, the angle, the direction it's causing it to rotate, and the point at which it's being applied. So let's kind of draw out an illustration here. And let's say I have a rod. And let's say this rod is fixed here on this left end. Okay, so that's going to be my pivot or my axis of rotation. Now it's real important. The first thing you should always do is to identify where is your axis of rotation. And then let's say we have some kind of force that's pushing upwards on this right side of the rod. Now, identifying that axis of rotation, that's real important. So if its axis of rotation is on the left end and I'm applying a force upwards on the right end, that means that this rod would then rotate counterclockwise. And so that means it would be a positive torque because it's causing it to rotate counterclockwise. Now, the last thing that we had wrote on there is that it depends on the point at which it's being applied. So that point is a measure from your axis of rotation to wherever the force is. And we use the symbol R. Now that's not radius. That R stands for a moment arm. And again, it's just a measure. It's a distance from your axis of rotation to the force. And we need to have that in meters. Now, one thing to make note is that only the perpendicular force will cause torque. Okay, so only the perpendicular force causes torque. So let's kind of see what that looks like. Let's say we have another rod. Again, let's say this axis of rotation is here on the left. And let's say this time I have a force that's at an angle. Since it's at an angle, the whole force is not causing torque. It's only the perpendicular portion. So if I made a little triangle here, and let's say this angle here was given, it's only this perpendicular portion of that force that's going to cause torque. Okay, so we got to use our trig functions and solve for that perpendicular side of that triangle, and then that's going to be the portion of the force that is causing torque. And our equation for torque is tau, Greek symbol tau, is equal to that moment arm times the perpendicular force. And the moment arm is in meters. Force we know is in Newton, so torque is just in Newton meters. And that's going to be our unit for torque. Now, one thing to make note is that your Fg, right, the gravitational force, it does cause torque, right? It applies torque, but only at the center of mass. So let's say now we have a rod and this time my axis of rotation is right here in the center. And Fg is always at the center of mass, so I would draw Fg. So in this case here, my moment arm, the distance between the axis of rotation and the force, would equal 0. So that means in this case, torque, there would be no torque caused from the weight of this rod. But in this rod where the axis of rotation was on the left, we would have an Fg going down. So in this case, the weight of the rod would cause torque going in the clockwise direction. Okay, so don't forget about your Fg. When you have a rod that we're looking at or an object that's rotating, always draw in your Fg to make sure to see if it is causing torque or not. Now we're going to see a lot of similarities with forces and when we're working with forces and also with torque. And so if you remember back, one of the first units of the year we had was our statics. And so that's whenever we were in static equilibrium. Well, these notes are called static torque. Okay, so now we're going to be in static equilibrium in terms of our torque, so we would call that rotational equilibrium. Now, last semester, when we said an object was in static equilibrium, that meant that my net force was equal to 0. For rotational motion, that just means that my net torque is going to equal 0. And so we're in a static situation. So that means that all of my torque would equal 0. So let's go ahead and let's work some practice problems here. This is number 1 on your static torque 1. And for this one, for number 1A, it's giving me this meter stick. It tells me each line is 10 centimeters or 0.1 meters. And it has different forces acting on it. And for this one right here, we're just going to write our net torque equation. So just like we did in our forces unit, and we made a net force equation, we're going to make a net torque equation. So to start out, let's call this force, we'll call torque 2, and this one we'll call it torque 1. Always draw in your Fg. And let's go ahead and make our net torque equation. So my net torque equation is going to be the torque caused from this force, F2. It's causing it to rotate counterclockwise. So it's going to be positive. So I'll write that one first. So torque 2 minus the torque caused from F1. And it's minus there because going up on the left side, since the center is my axis of rotation, it's going to cause it to rotate clockwise. So it's going to be negative. So that's why we put it minus in our net torque equation. And we're going to go ahead and write in minus torque caused from that gravitational force. But looking at this, we know that the moment arm for this one is equal to 0. So torque from the weight of this object is going to equal 0. So we can just kind of cancel that out there. Now they told me that each dash was 0.1 meters. So we can go ahead and go a little bit further with this net torque equation. So the torque caused from F2 is just going to be R times F2 minus R F1. And counting our moment arm for this first one, for F2, we have 0.1, 2, 3, 4, 5. So my net torque equation is going to equal 0.5 meters times F2 minus, now let's count our moment arm for that F1, it's 1, 2, 3, 4. 0.4 meters times F1. And now we have a net torque equation that we could work with. So that's a general first step in solving these torque problems is 1, identify your axis of rotation. 2, don't forget to draw in your FG. And from there, we build our net torque equation. Okay, to figure out which direction it's going to rotate for each force, counterclockwise, clockwise. That determines my positive and my negatives. And then we can make our net torque equation. So let's go on to number 2A. And so now for this one, we know those two forces here. And what we're going to do for each of these is show that the sum of the torques is equal to 0. In other words, we're in that rotational static equilibrium. So let's look at this. We have a FG down. Again, it's going to be at the axis of rotation, so that's not going to cause any torque. So we just have the 2. This one would cause it to rotate counterclockwise. This one would cause it clockwise. So this one's going to be positive. This one's going to be negative. So let's go ahead and make our net torque equation. And let's call this one 1 and this one 2. So the torque from 1 minus the torque from 2. Let's go ahead and plug in for those. So my net torque is equal to R times F1 minus R times F2. So for the first one, we have 1, 2, 3, 4, 5. We got 0.5 meters times that force, which is 32 newtons, minus, now we got 1, 2, 3, 4, 0.4 meters times 40 newtons. So my net torque is going to equal 16 Newton meters minus 16 Newton meters, which is equal to 0. So now we've shown that the net torque is equal to 0. So let's go on to number 3. And now for number 3, what we're going to do is we're going to solve for the missing force. Okay, so we have a force that's missing. Now we're going to solve for it. So first, identify your axis of rotation, draw in FG, figure out the direction. So this one's going to be positive, this one's going to be negative. Now we can build our net torque equation. We'll call this one 1, this one 2. So the torque from 1 minus the torque from 2. Our Fg here does not cause torque because my moment arm is 0. And it tells us that it's in static equilibrium, which means that we can set this equal to 0. And since it's equal to 0, that means the torque caused from the first one has to equal the torque from the second. Now we can plug in our equation for torque. And let's plug in our moment arms and then that one force that we know. So 1, 2, 3, 4, 5. So I got 0.5 times that unknown force is equal to 0.4 times 60 newtons. I'm going to divide both sides by 0.5. So that unknown force is equal to 0.4 meters times 60 newtons divided by 0.5 meters. So my meters cancel. And then this unknown force then is equal to 48 newtons. So you should be seeing some similarities to our forces unit. In our forces unit, we'd made net force equations. We made free body diagrams, and then we could solve for some kind of unknown force. The same thing applies here. We make net torque equations, and then we can solve for an unknown force. Let's go ahead and go to this last example here. And now we have some that are at angles. Okay, and so we have one over here on the left. It's 24 newtons at a 30-degree angle. We have another one, 20 newtons, that's at a 30-degree angle. And we're going to show that the sum is equal to 0. Now, first step, check your axis of rotation. It's not in the center now. So that means that at the center of mass, we do have some torque, okay, because the weight of it is no longer at the axis of rotation. Okay, so that's why it's always important to draw in your Fg, because you could miss that, that torque there that we have acting on this. So real quick, let's figure out our directions. Since the axis of rotation is on the left, that means this one would cause it to go counterclockwise, so it's going to be positive. This one over here would cause it to go clockwise, so it's going to be negative. And Fg will cause it to go clockwise, so it's going to be negative as well. So my net torque equation would equal, let's call this one 1, this one 2, and this one would be the torque caused by the gravitational force. So it'd be torque from 1 minus torque from 2 minus the torque caused from that weight of that object. So we're trying to show that it's equal to 0. So we're just going to solve for all these torques, and then we'll plug it into that net torque equation. So remember, it's only the perpendicular force that causes torque. So this angle here is 30 degrees. I know my hypotenuse is 24 newtons. So I need to solve for that perpendicular, that opposite side there. So I would use my sine function. So for the torque from this first one, which is equal 24 newtons times sine 30 degrees. Because it's only that perpendicular force there that's causing torque. Oh, we almost forgot the moment arm. Okay, so it's also times the moment arm, which is 1 meter. And so if I plug that in, it would equal 12 newtons times meters. And for torque caused by that second force, it's going to be that moment arm, which in this case is 1, 2, 1, 2, because our axis of rotation is over here on the left. So 0.2 meters. And we're going to use that same trig function there to solve for this perpendicular side. So we're going to use our sine function again. So 0.2, 20, sine 30. And if we plug that in, the torque from this one is going to equal 2 newtons times meters. And then lastly, we've got to find the torque caused from the weight of this meter stick. And so now my moment arm is going to be 0.5 because it's at the center of mass, so 0.5 meters, times the weight of this object. And so it's 2 kilograms. That means the weight is 20 newtons. So the torque caused from that gravitational force is equal to 10 newtons times meters. And lastly, we were showing that the net torque was equal to 0, so we're going to plug it back into this equation. So your net torque is going to equal 12 newtons meters minus 2 newtons times meters minus 10 newtons times meters. So my net torque is equal to 0. So to kind of sum everything up, and general steps here in solving some of these problems is 1, identify your axis of rotation. Once you do that, draw in the weight of the object so you don't forget about that torque. And then you can build your net torque equation, and from there you can start solving for whatever it is the problem wants you to solve for, whether it's an unknown force or something like that.